To begin with, we have this differential equation, which is the double derivative of y minus 2y prime plus y equal to e raised to t, with initial values of y of 0 equal to 0, with y prime of 0 equal to 5. First, we have to separate by terms this differential equation to be able to extract the Laplace transform of each term. In this case, we separate it in 4 terms, and directly we put the result of this. For the transform of e raised to t, in the formula it says that we transform of a e raised to at is equal to 1 over s minus a, where a will be the coefficient of t. And as t is implicit with a1, a is equal to 1. And finally, the next step is to multiply everything and simplify all where y is going to be 0, and where y prime is seen is going to be 5. And the result will be like this: s squared minus 2s plus 1 all multiplied by y of s minus 5 equals the transform of a to t, which will be 1 over s minus 1.
Okay, now we continue with this equation that we have here. We have square s minus 2s plus 1 by capital Y of x minus 5. All of this is equal to 1 over s minus 1. Okay, so as we have the negative 5 here, this crosses the equation to the other side as positive, okay? And then we have the square s minus 2s plus 1. As is multiply the equation to the other side, it crosses as a division, okay? So we have all this equation of here, okay? And then for find or for search or look the inverse Laplace transform of this equation, we can simplify or we can simply the equation, okay? So for that, as the two fraction has the same denominator, we can put them together, okay? So we can 1 over s minus 1 plus 5, all of this over square s minus 2s plus 1, okay? So for establish the equation, for make it more simply, we can add an s minus 1. Remember that we have we can add to the s minus 1 in the numerator of the 5 and the denominator of the 5 as s minus 1. For that reason, we have all together here, okay? And then we can multiply this s minus 1 with the denominator, and we have all of this, okay? We have 1 plus 5 by s minus 1, and in the denominator we have s minus 1 by square s minus 2s plus 1, okay? And then remember the distributive property that the 1 will multiply this 1 and the s. This is a s, okay? And the 5 will multiply the s and the minus 1. That is a negative 1, okay? Now, after after do the distributive property, we have 5s minus 4 over s minus 1 by square s minus 2s plus 1, okay? And having this, we can make the equation more simply, okay? So then we can factorize this square s minus 2s plus 1. Remember that for that we can find, or we have to find, and two terms that multiply will get us the square s, okay? That they are s plus s by s, sorry. And the same for the 1, and we have the minus 1 minus 1, okay? that multiply, they are 1, okay? So then, remember that we multiply in a cross way, so we can minus s, okay? So this is um, this operation will get us minus 2s, that is the term that we have here, okay? So now we have the two terms, that is s minus 1 by s minus 1, that is the one term that we have here, okay, that we get from the factorize. So then we have the capital Y of s is equal to the negative or the inverse Laplace transform of 5s plus 4 over s minus 1 elevated to the cube. Okay, now for start to find the inverse Laplace transform of the question, uh, we have, remember, we have 5s minus 4 over cube s minus 1, okay, and we need to get the partial fraction of this term, okay, and then we have a0 over s minus 1 plus a1 over square s minus 1 plus a2 over cube s minus 1, okay, is the level of each s minus 1. For that reason, we have one s minus 1 here we have s minus 1, and here we have s minus 1 three times, okay. Then for for have all the equation in a linear form, we add a cube s minus 1 in this side of the equation and if this side of the equation too, okay. And then for that reason, each term has a cube s minus 1, okay. So we can start to um, eliminate the things, the denominator for have everything in a linear form, okay. So then we can eliminate this with this, we can eliminate this s minus 1 with one of the three s minus 1 that we have here. We can eliminate this square s minus 1 with two of the three s minus 1 that we have here. And finally, we can, as here, we can eliminate this cube s minus 1 with this cube s minus 1, okay? Then we have 5s minus 4, it's equal to a0 by s minus 1 to the square plus a1 by s minus 1 plus a2, okay, and we can take the a2 as a 1, okay, as a 1 because there is just one a2. Then here you can see that we have a square binomial, and we have to express it as we have to elevate as s minus 1 to the square, okay, and here we have to do the same property distribution that we saw before. Remember the a1 will be multiplied to the s and will be multiplied to the minus 1, okay, and we just change and we substitute the a2 with 1, okay. Then when we elevate s minus 1 to the square, we have the square s minus 2s plus 1, that is the same denominator that we had before, okay. And then with doing this multi, we have a1s minus a1 plus 1, of course, and then we have to multiply the same distribute property with this a0 will be multiplied to the s square and the minus 2s and the 1, okay. When we do these operations, we have 5s minus 4 equal to a0 square s minus 2a0s plus a0 plus a1s minus a1 plus 1. Okay, and then for find the values for a0, a2, and a1, we have to put together the in this side of the question we have to put together the the terms that don't have a s, that just they are. Okay, so here we have the a0, this minus a1 and the 1, so we have this in brackets. Okay, and remember that this is from this side of the question. And then we have to find the terms that have s, and we apply the similar terms. We have s, and in brackets we have this 2 minus 2 a0s and the a1s. So remember, we apply the um, similar terms, and we have s, we have in the brackets minus 2a0 plus a1, everything of this multiplied by s. Okay, and we just have the a0 square, and then we go to this table, this little table, and we have this little question here that equal to 4, because uh, they are constant terms. Okay, constant terms. And here we have the term that had s, so this is equal to 5, because this s has 5 as coefficient. And like there is not a s square in this part of in this side of the question, the a0 is equal to 0. And then making the operation, we have that a0 is equal to 0, of course. We have that a1 is equal to 5. Okay, is equal to 5. And finally we have that a2 is equal to 1, as we have here. Okay, now using this equation that we used before for get the partial fraction, with the values that we have now of a0, a1, and a2, we can substitute these values in the equation. Okay, so we have 0 over s minus 1, that this will be cancelled. Okay, plus 5 over square s minus 1 plus 1 over cube s minus 1, and this is equal to this equation that we have here, that is this equation but without the 0 over s minus 1. Okay, and then we can get, or we can find the inverse Laplace transform of this equation. We can divide it, or we can get the inverse Laplace transform of each term. Okay, so here I forgot to put the inverse Laplace transform of the second term. So wait a minute. Okay, almost is here. Okay, so then we can get, or we can find, or we can look the inverse Laplace transform of each term. So here we got the inverse Laplace transform of 5 over square s minus 1 plus the inverse Laplace transform of 1 over cube s minus 1. Okay, so the inverse Laplace transform of 5 over square s minus 1 is equal to 5 by e elevated to the t by t. Okay, using a software, you can comprovate this result. And the inverse Laplace transform of 1 over s the cube s minus 1 is equal to a elevated to the t by square t over 2. Okay, and finally the inverse Laplace transform of capital Y of s is equal to 5t by a elevated to the t plus at by square t over 2. And this is the final result. Thank you for watching.
Okay, we will start talking about the procedure of the exercise number 4. So first we have this function that is g prime plus 5 times g, and we have a conditional with say that when t is between 0 and 1 but no reaching to 1, this function we will are equal to t squared. But when t is greater than 1, the function are going to be equal to 0. This part can be written as a graphic, in a graphic, to understand more this statement, because we have that when the function is between 0 and 1, we have that the function are activated because they have a real value that is t squared. But when the t is greater than 1, the function comes to 0. So basically we can say that the function is activated when t is between 0 and 1, and when it's deactivated when t is greater than 1. Okay, this is a step unit, and the next step to resolve this problem is convert this condition into a form that we can apply the Laplace transform. So how we can see the function is activated when at the point in the origin. So we have the function that is t squared times the unit step related to the origin, that is t. So, and how the function is activated when the t is equal or greater than 1, this step is basically a displacement of the function by 1. So to make a relationship, we need to rest that displacement, that is t squared times the unit step, the t minus 1. So once getting the transform of this condition into a form and that we can apply the Laplace transform, so we need to apply the Laplace transform in both sides, in this one and this one. So how we can see the Laplace, the formula of the Laplace transform to derivate is this one, is n time Sn times the function minus Sn minus 1 times the function evaluate to 0, and well, this one. So the Laplace transform of G prime is GSS, because we have one aquí, one here. So S times the Laplace transform of G minus G evaluate to 0. And the Laplace transform of 5 times G is just 5 LG, because we have a 0 s 0 and it converts to 1, so 1 times 5 times 1, so it's 5. So is to reduce the equation. So this both we have this SLG minus G evaluate to 0 minus 5LG. Now we need to apply the Laplace transform to this equation. This this equation, that is t squared times the unit step of t minus t squared of the unit step of t minus 1. That is this. So basically we have 1, so t squared times 1 is t squared. So just apply the Laplace transform to t squared. Thus, well, the formula is very knowledge, so is 2 over s elevate to 3. And now we have that this formula, that is when we have a incógnita elevate to key times the function or any function. So we have this t squared times the unit step of t minus 1. So the formulas say that we need to apply this, that is minus 1 elevate to key times the derivative of key over ds of key times the Laplace transform of the function, just the function. So well, we have minus 1 square, because we have a t square, times the second derivative of the Laplace transform, that is this unit step of t minus 2 minus 1, sorry, minus 1. So applying the derivative and the multiplying the minus 1 square, we have this s squared plus 2s plus 2 over s elevate to 3 times e elevate to minus s. So in this part we just need to clear the g to get the form to apply the inverse Laplace transform, and well, get the answer of this problem. But in this part I just clear the g. So in the statement say that this when g is equal to 0, g is equal to 1. So well, this is 1, and just come to this part in the other side, and we have 1 plus 2 over s elevate to 3 minus this part. Well, now to finally clear the g, we have to factorize this part and this part. Why? Because well, we can see that here we have similar terms, g and g, and well, the different terms is 5 and s. So factorizing this part, we have s minus 5 times g. And to finally clear the statement, this part is just pass the s minus 5 to the other side. And then finally we have 1 over s minus 5 plus 2 over s elevated to 3 times s minus 5 minus s squared to 2s plus 2 times e elevated to minus s over s elevated to 3 times s minus 5.
Now we proceed to continue doing the step 2, which the realization of this inverse Laplace that we ourselves obtain from the normal Laplace. And to the begin to with we end up transferring these two, and transferring this a minus 3, and it becomes to positive to do the inverse rule, and we use the inverse Laplace until we reach this result. No, this result. And each of these we are multiplied by 5t, and the two that we are affected, and it is modified a lot to the path we had before. And now in this part is accommodate with the respect to the denominator and numerator that we have by powers. And so in the end we obtain the all results, which are the following, and this final result is this.